In this lab, we evaluated the boundary layer effects over a cylinder at different dynamic pressures, in addition to the effects of adding a tripwire. We hypothesized that our smooth cylinder closely follows the theoretical values of an inviscid cylinder, and that adding surface roughness causes the boundary layer to decrease the effects of drag. Applying our previous knowledge of pressure, we evaluated how the pressure reacts with an added boundary layer around the entire cylinder. In addition, we added tripwires to the top and bottom of the cylinder to see how those affect the boundary layer and pressure. Overall, our data showed that we followed our trends with some variance in our data. However, the biggest issue we encountered with Aero was the force of lift with respect to the Reynolds number. This showed an opposite trend than expected. We equated that this source of error was to be from faulty data and decided that this error is not significant since we are looking at a small change of force. All these parameters were used in our calculations and will be referenced in the following slides.
When testing flow visualization around a cylinder, it can be seen at mid to high Reynolds numbers the flow separates off the back of the cylinder. This happens because at these Reynolds numbers, the boundary layer begins to separate from the surface of the cylinder, creating pressure drag in a low pressure zone behind the cylinder. In order to keep this separation from happening, one can either increase the Reynolds number of the surface, which would involve either increasing the diameter of the cylinder or increasing the flow velocity, or by tripping the boundary layer separation by making the cylinder surface rougher. This can be done by attaching something like a wire or sandpaper to the surface of the cylinder in order to generate turbulence in the boundary layer and keep the flow attached as long as possible. A smooth cylinder of 0.1143 meters diameter was placed across the middle of the test section. Inside the cylinder in the center were 24 pressure ports, one for every 15 degrees around the surface of the cylinder. These pressure ports were hooked up to a 64-channel scanted valve pressure measurement system, so coefficient of pressure and pressure drag could be tested at 50, 150, and 300 RPM. Before any testing was done, the safety working procedure was gone through. We made sure there was a supervisor around to keep things under control, opened the garage door behind the diffuser, checked around the tunnel for loose items that could potentially become hazardous, closed the doors to the wind tunnel area, and put up red flashing lights to warn people outside that the test was about to be done. We then made sure the test section was clear of potentially hazardous or loose materials, then closed and locked the doors, and then verbally warned others inside the testing area that we were about to conduct testing. While we were testing, smartphones, specifically iPhones and the Samsung Galaxy S7, were used to record flow visualization around the cylinder in slow motion to get an idea of exactly how the separation off the back of the cylinder looked. In order to visualize the flow, a fog machine was placed at the inlet to show how the airflow was moving through the wind tunnel over the cylinder, and a low-power laser was placed above the wind tunnel, pointing at the flow immediately behind the cylinder to better see the flow separation. The cylinder was then set up to trip the boundary layer by attaching two very thin wires to angles 45 degrees above and below the incoming flow direction using aluminum tape. Pressure drag and flow visualization were then recorded again with the boundary layer tripwires in place at the 3 RPMs. After this test, another two boundary layer tripwires were installed at 90 degrees normal to the flow direction above and below the cylinder, and again pressure drag, coefficient of pressure, and flow visualization were recorded.
Here are some of the equations we used in our results. We also used Reynolds number, and we used Reynolds number in our flow visualization to determine if the boundary layer is transitional, turbulent, or laminar.
These three graphs show the coefficient of pressure at different RPMs. The different colored lines on each plot correspond to the different trip conditions. The blue lines on each graph are the theoretical and viscid solution. In real life, the boundary layer around the cylinder causes non-ideal effects. The middle peak of the inviscid solution is cut off by the real data because there is an area of low pressure in the wake. This peak corresponds to the side of the cylinder facing away from the flow. The point where the data starts to deviate away from the theoretical solution is where the flow separation occurs. At about 1 radian, this happens for all the plots. During all 3 RPM tests, the 45-degree trip, which is the yellow line, is shown to cause the flow to separate at a greater angle on the cylinder, meaning that the wake region behind the cylinder is smaller. In addition, the wake region has a higher pressure when the 45-degree trip is applied. It is worth noting that the 45 and 90-degree trip does cause the flow to separate later, but the coefficient of pressure in the wake region is the same as the smooth cylinder. These plots compare the effects of the trip condition at different RPMs. The colored lines correspond to different wind tunnel RPMs. Note the no trip graph on the left shows the flow separates much sooner. The absence of the fangs, which are the minimum peaks on the graphs, are evidence of this. Lower Reynolds numbers, which are the red lines in all the graphs, cause the wake region to have a higher pressure. The flow is able to fill in the wake region more when velocity is less. The largest fangs occur on the 45-degree trip graph in the middle. The flow stays attached to the surface of the cylinder the longest here. When both trips are applied on the right, the flow also stays attached longer. However, the pressure in the wake region stays lower. This is because the 90-degree tripwire induces flow separation. There is certainly some error here worth noting. The jaggedness of the red lines indicate that the pressure sensors are less accurate when the readings are lower. Our group also dropped the cylinder after the no-trip data was collected. The higher RPM no-trip data is much smoother than the data at the same RPMs after we dropped it. The tripwires cause turbulent flow, but dropping the cylinder must be mentioned as a source of error. These graphs show different conditions affecting the coefficient of drag. The 45-degree trip reduced the coefficient of drag as anticipated at higher Reynolds numbers. What wasn't expected was how the coefficient of drag is affected by the 45 and 90 trip. The graph shows that it increased the drag at low RPMs and decreased the drag at higher RPMs. This could be due to the fact that at low RPMs, the extra 90-degree tripwire increases the frontal area and induces flow separation. When comparing each trip condition to the Reynolds number, it becomes apparent that tripping the flow at 45 degrees helps reduce drag at even more at higher Reynolds numbers within our range of laminar flow. The 45 and 90-degree trip follows the same pattern as the smooth cylinder. These plots represent the most important results of the lab. The force of drag is obviously smaller when the flow is tripped at 45 degrees. The graph on the left shows this as all of the middle points are lower. It is also obvious that at higher Reynolds numbers, the more the drag dips when the tripwires are added. Yellow dots on this graph show how much the force of drag decreases at high RPM. Again, there is no benefit of adding another tripwire at 90 degrees compared to just 45. The right graph shows the exponential increase of the force of drag with Reynolds number. The 45-degree trip, the red dots, show that this is exponential and the increase is significantly reduced when this trip is added. The force of lift is essentially drag force normal to the flow. In a perfect world, all of these numbers would be zero, but lift is still minuscule compared to the force of the drag. Negative values of lift correspond to downward pressure, and positive is an upward force. The error becomes even more apparent at higher Reynolds numbers. This is caused by a few different factors. Variation in the orientation of the cylinder can have a big effect. If the angle is assumed to be zero, but it actually points up or down, then the drag force will appear as lift force. The flow in the test section also may not be completely one-dimensional. The flow may come at the cylinder at an angle from the top or bottom. Lastly, it is quite possible that our tripwire on the top and bottom of the cylinder were not oriented at exactly 45 degrees.
The main goal of this experiment was to test the hypothesis that increasing surface roughness would cause the boundary layer to stay attached to the cylinder longer, decreasing the effects of pressure drag and keeping the flow more attached off the back of the cylinder. The initial cylinder's flow followed theoretical values very closely, and adding the first tripwires at 45 degrees supported our hypothesis by causing the flow to separate later off the back of the cylinder and decreasing pressure drag. However, when the 90-degree tripwires were added, the frontal area of the cylinder was increased, inducing flow separation and increasing pressure drag. The coefficient of pressure measured during the experiment also did not exactly follow the envisaged solution because the pressure begins to increase at the shoulder of the cylinder and the force due to pressure begins to slow the flow, forcing some of the fluid in the boundary layer to stop or reverse direction, creating separation. It also cannot be assumed that the flow is envisaged because realistically we cannot make these assumptions in experiments. Overall, it was seen that increasing surface roughness does indeed cause the boundary layer to stay attached to the cylinder longer, but one must be careful about placement of roughness so that the nature of the cylinder to the oncoming flow is not changed.